Hey everyone, I hope you're doing well today. In this video, let's talk about position, velocity, and acceleration. And just so you're aware, while there are problems that need integral calculus for position, velocity, and acceleration problems, the problems in this video won't need integral calculus at all. Whether you're taking calculus right now, or studying or preparing for the AP exam, or you're just simply excited and just interested in learning about these concepts, I hope you find this video helpful. And if you do find this video helpful and you don't mind clicking that like button, it really helps out this channel grow and support the nonprofit that this channel is linked to. Now let's talk about some background information before we get into a couple examples together. For starters, our position function is typically represented by x of t or s of t, where t represents time. Our velocity function is typically represented by v of t or x prime of t, or the first derivative of the position function. And our acceleration function is typically represented by a of t, x double prime of t, or v of t. X double prime of t just represents that acceleration is the second derivative of the position function, and v prime of t just lets us know that acceleration is the first derivative of the velocity function. Looking at the progression of the x of t function, we can see that we have x of t, x prime of t, and x double prime of t. While velocity represents the first derivative, acceleration will represent the second derivative of the position function. Now, it's important to understand that whenever you have a negative velocity, it means the particle or the object that we're talking about in a problem is moving towards the left. On the other hand, when you find out you have a positive velocity, it means the particle or object is moving towards the right. A unique case you want to be aware of is that when the velocity function is equal to 0, but the acceleration function is not equal to 0, it means that the particle is stopped and is changing direction. Now, something really important to also know about the relationship between velocity and acceleration is that when they have the same signs, like they're both positive or they're both negative, then it means that the particle is increasing in speed. However, if they're different signs, like one is positive and one is negative, then the particle is decreasing in speed. And one more piece of information that may be helpful to know is that whenever you take the absolute value of the velocity, you find out the speed of the particle. Now that we've gone over some background information, let's get into some practice problems together. To get the most out of these examples, I encourage you to grab some paper, something to write with, and let's do some math together. Example 1. If the position of a particle at time t is given by the equation or function x of t is equal to t cubed minus 11t squared plus 24t, find the velocity and the acceleration of the particle at the time t is equal to 5. Now, while we know that the position function is x of t, velocity is going to be our x prime of t, or our first derivative, and the acceleration will be x double prime of t, or the second derivative. Taking the first and second derivative of the position function, here are each of those functions. Taking the first and second derivative of our position function, here you can see the functions for velocity and acceleration. And remember, depending on how the problem you're given is written, x prime of t is the same thing as v of t for velocity, and x double prime of t is the same thing as v prime of t, or a of t. Let's start by finding the velocity. We know we're trying to find out the velocity when t is equal to 5 or time is equal to 5, so let's substitute in 5 for t. Substituting in 5 for t and going ahead and solving this expression using the order of operations, we should find out that when time is equal to 5, or 5 seconds, the velocity is equal to negative 11. Try to remember from earlier that when the velocity is negative, like we have here of negative 11, that this particle is moving towards the left. Now let's find out the acceleration of this particle at time is equal to 5. Using our acceleration function, a of t is equal to 6t minus 22, let's substitute in 5 for t. Substituting in 5 in for t, we find out that at time t, the acceleration is equal to positive 8. At this point, we've solved for the velocity and the acceleration when time is equal to 5. Let's take a peek at what this looks like on a graph. Here we have the original position function x of t. If you look closely at the x-axis and find where time is equal to 5, and you draw that vertical line down to see where that is going to be on the position curve, you can see that when you draw a tangent line to this position function, that we're going to get a negative slope. this negative 11 that we found out for the velocity is just really the slope of the tangent line when time is equal to 5 on the position function. Hopefully this gives you a little bit of a visual understanding of seeing how the velocity is negative, so we can see it has a negative slope at this point, and we can also see that it's slowing down as the object is getting close to the bottom of this curve on the position function. Example 2. If the position of a particle is given by x of t is equal to t cubed minus 12t squared plus 36t plus 18, where t is greater than 0, find the point at which the particle changes direction. Then find the interval of time during which the particle is slowing down. Just like the last example, we're given the position function and we're told that the domain or time is restricted to being greater than 0. When they ask us about when the particle is changing directions, remember that this is when the velocity is equal to 0 and the acceleration is not equal to 0. What about finding the interval of time when the particle is slowing down? Do you remember when that happens? If you were thinking that that was when the velocity and acceleration have opposite signs, then great job. And if you had no idea or you just simply forgot, no worries, you can always just scroll back to the beginning of this video and check out each of those circumstances. Just to get organized and have all our functions ready to go, I'm going to find out the v of t and a of t, which is just the first and second derivative of the position function. Let's start by finding out when this particle changes direction. So when the velocity is equal to 0, we can just write the equation v of t is equal to 0. Swapping out v of t for 0, we can set 3t squared minus 24t plus 36 equal to 0. Hopefully this looks familiar because it's just a quadratic equation. To find out when the right side is equal to 0, remember that you have a few options like factoring, completing the square, or using the quadratic formula. Let's see if we can try factoring. First, to get smaller coefficients, we're going to divide both sides by 3, and we get 0 is equal to t squared minus 8t plus 12. And lucky for us, this is factorable, so we can write this as 0 is equal to the quantity of t minus 6 times the quantity of t minus 2. The two times when the velocity function will equal 0 is when t is equal to 6 and when t is equal to 2. Now that we found out when the velocity is equal to 0, let's check out when the acceleration is not equal to 0. Our acceleration function is a of t is equal to 6t minus 24, and let's set it equal to 0 to find out when we don't want the time to equal 0. Going ahead and solving this linear equation, we find out that the acceleration will equal 0 when time is equal to 4. We just found out that the only time the acceleration will equal 0 is when time is equal to 4. That means that when the time is not equal to 4, like when time is equal to 2 and time is equal to 6, the acceleration does not equal 0. Therefore, we can conclude that the particle changes direction when time is equal to 2 and when time is equal to 6. So we just finished finding out when the particle changes direction, so let's try finding out when the particle is slowing down. The particle will be slowing down when the velocity and acceleration have opposite signs. Using the three critical points we just found for when velocity is equal to 0 and acceleration was equal to 0, let's set up a table. Given that the problem only wants us to consider when time is equal to 0, let's set up the following intervals using that fact as well as our critical values. Let's take a look at this first interval of when time is between 0 and 2 seconds. While you can go ahead and pause the video and try this on your own, I'm just going to go through these and choose some easy values. I'm going to choose t equals 1, and when t is equal to 1, you can find out that the velocity is going to be positive, and when t is equal to 1 for the acceleration function, you'll get a negative value. For the second interval, when t is between 2 and 4, I'm going to try the value t is equal to 3. If you were to substitute in 3 to the velocity function, you would get a negative value, and if you substituted in 3 for the acceleration function, you would also get a negative value. For this next interval, when t has to be between 4 and 6, I'm going to try substituting in the value of t is equal to 5. In the velocity function, if we substitute that in, we're going to get a negative value, and if we put in t equals 5 for the acceleration function, we get a positive value. And for this last interval where t is greater than 6, I'm going to plug in the value maybe like 7, right? So when t is equal to 7, substituting in, we will get a positive value for velocity, and we would also get a positive value for the acceleration. While I didn't go over each of the steps of substituting in each of the values to find out when the velocity and acceleration were positive and negative, feel free to pause the video and go ahead and try it out for yourself just to get some confidence and make sure that they are correct. Now that we know when the velocity and the acceleration are positive and negative, let's check out the intervals where they have opposite signs so we can find out when the particle is slowing down. It looks like when time is between 0 and 2, we have opposite signs, and when time is between 4 and 6, we also have opposite signs. We can now conclude that the particle is slowing down between 0 and 2 seconds and between 4 and 6 seconds. Now let's check out what this looks like on a graph. Here's the graph of our position function, or x of t. To show you where the critical points are, here's where t is equal to 0, t is equal to 2, t is equal to 4, and t is equal to 6. Hopefully you can visually see that the particle is changing directions at t is equal to 2 and t is equal to 6 at that top and bottom part of the curve. And looking at this purple highlighting, it's important to notice that as the curve is getting closer and closer to t equals 2, the object is slowing down, and when t is getting closer and closer to t is equal to 6 on the left side, it is also slowing down. Hopefully by showing you this graph, this gives you a better visual understanding of what our answers really represented. And there you have two quick examples on some calculus problems on position, velocity, and acceleration. Once again, if you found this video helpful, it would really help out this channel if you could give the video a thumbs up, maybe even leave a comment, and consider subscribing. And if you'd like to see more of these types of problems, let me know in the comment section down below on what topics, and I'll try to get around to helping you out. As always, keep up the great work, and I'll see you in the next one.